Alright, you guys are looking at video E4.1-3 for the notes on aquifer terms. We just took some notes on groundwater and aquifers, and now we're going to look specifically at some of the terms that we're going to need to be able to talk about what's going on in the model aquifers that we're about to build. So, should be looking at this sheet right here. Again, E4.1b explained the features and process of groundwater systems is our focus right now. Okay, so I'm going to get this PowerPoint started. And I'm going to it's right here for you, and you can certainly use that pause button. So my little disclaimer here, aquifer terms can be necessary for you to learn most of these probably, so that we can talk about the aquifers. We expect to use this type of language and these terms when presenting that model aquifer. It's really the only way that this is going to make sense to you and us. So first off, the unsaturated zone is what you've heard it called so far. It's also called the aeration zone or zone of aeration. What we're talking about here, you guys, is from the surface down to the water table. Notice over here on the right-hand side, unsaturated zone is called the zone of aeration because the spaces are filled with air, but can be filled with air and or water because water passes through this region. It passes through down to the water table here. Okay. A cone of depression. When we pump a well, around that well, we get, if the water table is like this, as you pump, it's going to go like that. Think of drinking a milkshake with a straw. After it warms up a little bit and you're actually able to drink that milkshake, when you suck on the milkshake, you can actually see a cone of depression forming. Okay, you might have to get the drink down a little bit, but you can see that cone of depression forming. And the same thing is happening when we pump a well. You can see that right here. This is a cone of depression. It happens around a well. A confining layer is impermeable. So it says geologic material such as clay or granite with little or no permeability. So it is impermeable. In this particular diagram, we have two confining layers. You see the impermeable rock above the aquifer and below the aquifer in this case. Those are confining layers. Solid granite we consider to be impermeable. And clay. This clay is so tightly packed. Water will ultimately move, I guess, through either one of these, but we're talking on the scale of hundreds or thousands of years for this to take place. Depletion. It says the loss of water from surface water reservoirs at a rate greater than that of recharge. So our output, what we're taking out, is greater than the input. Discharge is greater than recharge. Okay, and we can see that we have overpumped these wells. Our poor fish is now dead, or on the ropes perhaps, and we have depleted our aquifer. We've even dried up this well right here. Discharge, an outflow of water from a stream pipe, groundwater aquifer, or watershed, just the opposite of recharge. Discharge is taking out of the aquifer or from the water system. Recharge is putting back into that particular system, whether it's groundwater or surface water or whatever. So I want to differentiate between cone of depression, which is that cone, so that V around a well that we get when we pump it, versus drawdown, the lowering of the water table. So on the left-hand side, we see this cone of depression. We go ahead and we overpump that sucker, and on the right-hand side, we have lowered the entire water table. That is drawdown. Drawdown is the lowering of the water table. Cone of depression is what happens naturally right next to that well when we pump it. Flow rate is the time required for volume of groundwater to move between 2 points. Okay, so how fast is it moving from point A to point B over a given amount of time? That's a rate. Distance over time. Typically groundwater moves pretty slow. We're talking inches per year, 2-3 inches per year. Of course, it certainly depends on the substrate or the strata, whether it's gravel or sand or something like that. It will have some different flow rates. An impermeable layer, like a confining layer, same thing, a layer material like clay that water can't go through. It's impermeable. Infiltration, flow of water from the surface, right here, down to the water table. It's infiltrating through. Over withdrawal. So think of the bank account here, you guys. Can't take out more than is going in. So it says withdrawal of groundwater over a period of time that exceeds recharge. Also referred to as overdraft or mining the aquifer. If we're mining it, we're not putting it back. It's kind of like mining for gold or another precious metal or diamonds. We're not putting it back, we're taking it. Okay. In this case, this particular aquifer is being mined. It's over withdrawn, and we have dropped that water table and ruined one well and a stream ecosystem here. A permeable layer is the opposite of impermeable. Permeable means it's porous, water can move through it. It has to be permeable so that we can call it an aquifer. If it's not permeable, if it's impermeable, it's not going to be an aquifer because there's no water in it. We could not put a well in it and get water. So in this case, looking at a diagram here, the sand and gravel, any of this is permeable. It is our aquifer. A plume, you've heard me use this term on several occasions, underground pattern of contaminant concentrations created by the flow or the movement of groundwater in a particular direction. So what we see here is a home. On the right hand side we see their well down here. We see this nice cone of depression for being in that aquifer. This line here would be the water table. That's what forms that cone of depression. The gray area is the unsaturated zone, and the turquoise or green area here is the saturated zone or groundwater zone. And this happens to be their septic tank and their drain field. So their wastewater coming out here, and we can see that it is actually moving towards their well. Whoops. It was either too close, so it's getting sucked in, or they're on the wrong side of the house, and this sucker is actually upstream and going to move into their well, perhaps. That would not be good for those that are wondering. But it's the idea that I think I use the example of a red food coloring. If we put that in our model aquifers, we're going to be able to see that. The eye picks up the color red quicker than any other color. That's the reason stop signs are red, stoplights are red, things like that. Brake lights, it's important. It is the fact that we pick up red, so we're going to use red because we're going to be able to see that plume move very, very easily. We'll be able to pick it up moving through our aquifer.